So this is a video on approximate integration. Sometimes this is also called numerical integration. So as we have seen, integration is hard. We have learned many techniques for how to find antiderivatives. Some of them become very painful and they're not something that you really want to do by hand. So we've also learned how to use technology like Maple or Wolfram Alpha or what have you to find antiderivatives. But even then, not every elementary function has an elementary antiderivative. So there are functions that even if we ask the best computer, it will not be able to tell us an antiderivative that we're going to be able to use. It's not going to tell us an elementary antiderivative. So what do we do when all else fails? We use approximate integration. These are ways of finding a definite integral. So we're going to be talking about definite integrals today. It has limits of integration. And when I say finding, I guess I just mean approximating it. So we're going to estimate these things. We're going to say, oh, it's about this number. And what good is that answer? Well, it's part of what we're going to learn today is how large the error can be. So that can be very useful information. Like if you ask me a question and I just say, oh, the answer is about this, what does about really mean? It doesn't really mean anything unless I tell you what the possible error is. But we're going to learn that about the methods that we're going to use today. So there's a few things, a few rules that we're going to use. Of course, one thing that this should bring to mind is when we first ever started talking about integration at all, like in Calc 1, the only method that we had is approximating it. We had the left endpoint rule, the right endpoint rule, and sometimes we also talked about the midpoint rule. So let me remind you of that. The midpoint rule, here I have a picture of a function over an interval, and this is just the old method where we break my interval from a to b into a bunch of subintervals. So I'm going to call a x0, and then there's going to be an x1, x2, and then b is going to be xn. And of course, you get a better approximation the larger n is, and then these get very close together. But for the sake of my picture, I didn't draw them that close together. But what you do is, on each interval, I'm going to draw a rectangle. And the height of that rectangle could, like, there's various ways of choosing the height of that rectangle. For the left endpoint, you choose the height to be like the height of the left endpoint. So if I were using the left endpoint rule, I would draw this rectangle. If I were using the right endpoint rule, I would draw this rectangle. It would be this high. So like it would match the right endpoint. But what I'm going to do is I'm going to use the midpoint rule. So let me just estimate where the midpoint is, draw my way up, and then this is how high that rectangle is going to be. And then likewise for the next subinterval, I say the midpoint is maybe here, and then so the height is going to be like this. Anyway, I do that all the way through, and then I add up the areas of these rectangles. And of course, that's just an approximation because these rectangles, that like there's this little corner of area that probably shouldn't be included, but I'm going to include it. And then there's like this bit up here, this little bit of area that I should include, but I'm not including. But this is just an approximation. So what estimate do we get? Well, this is the exact area, and the estimate that we're going to get by adding up the areas of the rectangles. Of course, a rectangle is just the area is base times height. These all have the same base. Like if I drew these subintervals all to have the same width, then these rectangles all have the same base. The base is what we call delta x. if I'm breaking up an interval and the interval goes from A to B and I break it up into n pieces, the length of each piece is going to just be the length of the whole interval divided by n. So these all have the same base. So if I'm adding up base times height, base times height, base times height, I can just factor out the base because it's all the same. And then I'm just adding up all the heights. And what are the heights? Well, the first rectangle has a height of whatever f of the midpoint is. So I'm letting x sub I bar be the midpoint, that's the average of the right endpoint and the left endpoint of the ith interval. So x, yeah, maybe I can, x1 bar is exactly halfway between x0 and x1. x2 bar is exactly halfway in between x1 and x2. So these are the spots where we're drawing a height of a rectangle, and we add up all the heights, and that's what we get. Okay, that's the midpoint rule. And I just put a box around this because this is the formula. The next rule we're going to learn is called the trapezoid rule. So this is going to use a slightly different method. I drew a picture that looks pretty much the same, or I meant for it to look the same. On this one, so we break it into a bunch of subintervals just like before, but I'm going to use a different shape to approximate each subinterval. In particular, well, I'm going to use a trapezoid. And more precisely, for my first subinterval, I draw a line straight up from the left endpoint, a line straight up from the right endpoint, and this is my trapezoid. A trapezoid is a shape that has two parallel sides. The other two sides need not be parallel. So this is the shape that I'm going to use to approximate the area for this first subinterval. And then I just keep doing that. For the interval that goes from x1 to x2, draw this, and then a straight line from there to there, and I have another trapezoid. So I keep doing this all the way until the end, and then I'm going to add up the areas of the trapezoids. Well, what is the area of a trapezoid? In particular, if I have a trapezoid that looks like this, which this is what I have, like the bottom is flat, and then I have basically there's the height on the left and the height on the right that are typically different. The area of a trapezoid is, I can write it this way. It's the base b times the average of the two heights, like the height on the left and the height on the right. So I'm going to add up the areas of all these trapezoids. So the area of my first trapezoid is here. The base is delta x again. It's the same delta x from before. Delta x is just the width of the intervals. So that's my base, and then I want to multiply the base by the average of the two height, like this height and this height. So this height is f of x0. This height is f of x1. So I get this. This is the area of my first trapezoid. Similarly, this is the area of my second trapezoid, and I just wrote dot, dot, dot. We continue that until we're done. Now let's simplify that and get this formula. So all I do is I pull delta x out of everything, because everything has a delta x on it. Everything also has a 2 on the bottom, so I pull that out. And then what do I have? Well, all the delta x's are gone, all the 2's in the denominator are gone, and then what do I have? I've got an f of x0, and then I have two f of x1's. There's one here and one here. And then I would also have two f of x2s. There's this one, and then the next term that I didn't write would have an f of x2 plus f of x3, so there would be two of those. In fact, all the ones except for the very first one and the very last one are going to get doubled up. So the pattern is I only have one f of x0, I only have one f of xn, and I've got two of everything else. So that's the formula for the trapezoid rule. One more rule that we're going to learn today is Simpson's rule. And I'm not going to do so much work to derive this rule. I'll sort of tell you the theory behind it. But for Simpson's rule, and first of all, it's important that n is even. Like the number of subintervals that we're going to break this into is even. Because what we're going to do is group these subintervals in pairs. So like I'm going to lump x0 all the way to x2 together. And then I'm not going to draw this because I'm not a great artist. The picture would look terrible, but for the just to remind you, for the trapezoid rule, it's like I'm using a straight line for each piece. For Simpson's rule, I use a parabola. Like I find a parabola that goes through this point, right above x1, and this point right above x2. I find a parabola, and this gives a better approximation because, roughly speaking, parabolas are curvy. Parabolas do a better job of lining up with the curve. Like, if I draw a straight line, it doesn't line up that well. A parabola does a better job. So what I do is I lump these in pairs. So I go from x0 to x2, I go from x2 to x4, all the way into the n. And by the way, this is essentially why n has to be even for this to make sense. I draw a parabola on each thing, and then I find the areas underneath these parabolas, and in theory that's easy to do. Like integrating a parabola is fine. We can do the antiderivative of any polynomial. That's no big deal. And I'm not showing you the details, but we add up all the areas underneath these parabolas and we get this. So let me say a word about this. This is the same delta x from before, just to remind you. It's just the width of the subintervals. That's the same for all of these. And then it's over 3, and then we have sort of a similar-ish looking thing to what we've seen before. There's a little bit of a funny pattern, though. My x sub 0, there's just one of those. And then, skipping to the end, f of xn, there's just one of those. And the ones in the middle are alternating 4s and 2s. It's not that weird of a pattern, but it's a bit strange. It starts with a 4. So yeah, let me start over. We've got a 1 in front. The very next one should be a 4. This alternating 4s and 2s, it always starts with a 4 and ends with a 4. So it's alternating 4s and 2s until we get to the second to last one, which should be a 4, and then the very last one is just a 1. And that's Simpson's rule. Okay. Let's talk about these error bounds, because an approximation basically doesn't do us any good unless we know how far away it might be. So here's the question. How far away could this, which is the exact answer to the integral we're trying to approximate, how far away could this be from the approximation that we get using these various rules? And the answer is different for different rules. So for the midpoint rule, the error is at most this, and I'm not going to justify this at all. This is beyond Calc 2 stuff, really. But the error is is at most this. And in other words, the approximation that we put could be this much above the real answer or this much below the real answer. It could go in either direction. And by the way, A and B are these limits of integration. N is just the number of subintervals. That's like this N. And what's K? Well, I'll tell you. K is a bound on the absolute value of the second derivative. K could be any number as long as the absolute value of the second derivative is at most K, at least as long as X is in the interval that we're talking about, from A to B. So as long as you can come up with a suitable number for K, you can put that here and find a bound on the error. So that's for the midpoint rule. The trapezoid rule is extremely similar. The error for the trapezoid rule is at most this. The only difference between this and this is this one has a 12 in the bottom and this one has a 24. So actually, the midpoint rule has a smaller error. Like putting a 24 in the bottom makes it smaller than the 12. So in a sense, the midpoint rule is superior. And of course, K means the exact same thing as it did. It's just F double prime. Absolute value has to be at most K. Then we get to Simpson's rule, which is a bit different. There's a couple of things going on here. This, like, I've got b minus a to the fifth instead of to the third, and I've got a 180 n to the fourth on the bottom. Other than that, K is also different. K does not mean the same thing as it did for midpointed trapezoid rule. It's something fairly similar, but it's the fourth derivative. When we talk about higher derivatives, we don't write like prime, 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 because that gets a little bit hard on the eyes. So we write parentheses, like this is a notation for the fourth derivative. So as long as the absolute value of the fourth derivative is at most K, for values of x from A to B, the error in Simpson's rule is at most this. All right. Let's use this for something. This is an example of a definite integral that we can't do the standard way. We can't really do this using the fundamental theorem of calculus. The fundamental theorem of calculus is, well, it's what you're used to. It's where you find this antiderivative and then plug in this and subtract. The trouble is, we will not be able to find this antiderivative in terms of any elementary function. This is one that we asked Maple how to do this. We asked Wolfram Alpha how to do this. They gave us this weird answer in terms of this ERF function that we have maybe we're not familiar with and we don't know how to use. So we're not going to be able to pull this off using the fundamental theorem of calculus. We can estimate it, though. We can estimate it, and let's say we want to use the midpoint rule, and just to make sure we get a reasonable estimate, we want to make sure that the error is at most 0.1. So we're using the midpoint rule. I just have to plug it into this formula, and I got a little bit ahead of myself. In order to use this formula, I need to know n, and how big n needs to be is, well, it's however big it needs to be in order to guarantee that the error is at most 0.1. So I ask myself, I'm using the midpoint rule. What do I know about the error in the midpoint rule? Well, we just talked about that. So b B is going to be 1, A is going to be 0, N we're trying to figure out. Let's talk about K. I need to make sure that f double prime, where f is this function, I need to make sure f double prime is absolute value less than or equal to k. Oh, let's find f double prime. So, all right, so f of x is this. To do f prime, I'm doing the chain rule. So derivative of e to the x is e to the x. And then I multiply by the derivative of the inside. Great. But what I wanted was the second derivative. So, well, now I have to do the product rule, right? So derivative of 2x is just 2, and then I'll leave the other part alone. And then product rule has two parts, so now I'm going to leave the 2x alone and do the derivative of e to the x squared, and now I find myself doing the chain rule again. Derivative of e to the x squared is e to the x squared times another 2x. Right? So this is 2e to the x squared plus 4x squared e to the x squared. All right. Now, what do I need from this? I need the absolute value of the second derivative to be less than or equal to k for, yeah, by the way, I'm just recalling this. For at least for values of x from a to b, which is 0 and 1. Now let's take a look at what we're dealing with here. E to any power is a positive number. And so here I've got a positive number. Here I've also got a positive number, right? X squared is always positive, and also x is from 0 to 1. So everything here is positive. So what I'm getting at here is these absolute values really don't do anything. Now let's think about how big this could possibly be, keeping in mind that x is between 0 and 1. So e to the x squared, that's going to be at most like whatever I get when I plug in 1. Like a larger power of e always gets bigger. So the largest this could ever be is if I plug in the largest possible value of x, which is 1. So what I would get is just e there. And then this is, so 4 carries through. X squared is at most 1 because x is at most 1. And this is at most e. So I get 6e. Everything here is approximate. Like I'm going to use a nice number for k. And what do I know about e without thinking too hard? E is like 2.7. In particular, e is less than or equal to 3. So let's just call that 18. So I can use k equals 18. by the way, what I just did feels a bit arbitrary, and it is. I could use any value of k that's bigger than this. I could use k equals 100 if I want. It's not really to my advantage to pick an absurdly large value of k just because I can. It'll end up being more work. But I'm fine just picking a reasonable value, something that like a whole number. So let's go with 18. So the error when we use the midpoint rule is at most, going back to this, 18 b minus a cubed over 24n squared. And what I want is the error to be at most 0.1. So let me call that 1/10, right? Okay, this is how we're going to figure out how big n needs to be. And then once I figure that out, I'm just going to use the formula for the midpoint rule. So let's solve this. Oh boy, I can cancel a 6 here, so this is like 3 over 4n squared. And I want this to be less than or equal to 1/10. Let me maybe cross multiply. So I've got 30 less than or equal to 4n squared. I want n squared to be at least, so I'm switching sides, so I reverse the inequality. 30 over 4, that's the same as 15 over 2. And I want to pick n as small as I can and guarantee that this is true. So this is like 7.5. So we can use n equals 3. We do want to pick a whole number for n for sure. Like n is the number of subintervals we're going to break it into. So n absolutely has to be a whole number. So I pick the smallest whole number that when I square it, I get something bigger than 7.5. So I'm going to do n equals 3. All right. So what does the midpoint rule tell me? I'm just using this. So first of all, delta x is b minus a over n. So 1 minus 0 over 3. My subintervals, so for the midpoint rule, I take my interval and I break it into n subintervals. So I'm going to take my interval from 0 to 1 and I'm going to break it up into 3 equal pieces. So my first subinterval starts at 0 because my interval is from 0 to 1. So I'm going to start at 0 and I'm going to go 1/3 of the way. And then my second subinterval is going to pick up where that one left off and go another third. And then I should have 3 subintervals and my last one picks up where the last one left off, and sure enough it's going to go another third, which should bring me to the end, and it does. By the way, in this terminology, this is my x0, this is my x1, of course it shows up in 2 spots, this is my x2, and this is my x3. I'm using the midpoint rule, so for each of these I'm going to find the midpoints. So, I'm using this formula x sub I bar is the average of these two. So x sub 1 bar is going to be the average of these two. It's the midpoint of these two, which is, I'll show the work. Just add them and divide by 2, but that's just going to be 1/6. x2 bar is the midpoint between these. So 1/3 plus 2/3 is 1, so I just get 1/2. X sub 3 bar is the average of these. So that's 5/3 over 2, which is 5/6. Okay, and we are getting very close to done, I swear. So this is approximately, I've got a delta x, so that's 1/3. And then I do f of x1 bar plus f of x2 bar, and then there's only one more, so there's f of x3 bar, because n is just 3. So here are my x bar values, and this is f of x, so I'm going to do, so f of x1 bar, that's e to the 1/6 squared. F of x2 bar is e to the 1/2 squared, e to the 5/6 squared. And to do this, I just used a calculator. And what did I get? I'll just leave it to 3 decimal places. This is only guaranteed to be accurate to within an error of 0.1. So definitely, yeah, maybe I should only leave 1 decimal place, because there's no guarantee like that these others are accurate. But I'll just leave it like that. By the way, I used a better approximation just to sort of get a better answer for this. I got 1.4626. So just like we promised, this is within 0.1. I guess that this one's a little bigger. The error approximation doesn't really tell you whether it's going to be bigger or smaller. It just tells me that the true answer is within 0.1 of this. It could be 0.1 above or 0.1 below. And the truth is, it's not even that far. It's like 0.03 above. Anyway, so that's how we do approximate integration. Of course, computers and calculators are much better at this. They can do a huge value of n and knock this out in no time. We took our sweet time just doing n equals 3, and in the end we had to use a calculator anyway. But this is what's running under the hood of a lot of calculators and computers when they give you approximate values for integrals.